All right, yeah, so my name is Günther. With me is my colleague Anoop. We are both part of Red Hat since a long time. Anoop is part of the Gluster community. I'm involved in the Samba project since many years. And I was maintaining the Samba package in RHEL, developing it for a long time together with Andreas Schneider. Now I'm switched to this other group where I look after this clustering solution based on GlusterFS on top of Samba and CTDB and Gluster. So we also are part of Michael's team. Michael now is really busy with many of the more modern container-based technologies. So we are now a much more smaller team. Also with us is Sachin, who's also giving a talk just after mine. We are presenting today a bit on not so much development efforts that we made, but we just wanted to share some of our experiences that we made in the past months with customer setups, with problems that people are having, with all kind of difficulties in understanding and then setup steps and configuration issues that customers and people are facing, and what the solutions to those are. So first of all, we just want to share some basic overview on the Red Hat Gluster storage solution, which is kind of the combined effort of all these open source projects. Then we want to dive a little bit deeper into these deployment issues that I've been mentioning, which boil down to clustering issues, to correctness problems in configuration, to performance limitations, which are partly part of Gluster itself, but sometimes also lay in the interaction between the Samba component and Gluster. And then finally, we want to, of course, share some lights about the improvements that we made, the upcoming development efforts that we are working on, and just sharing some outlook. Right, so the first set of slides are about Red Hat Gluster storage. So this is a kind of a product that Red Hat is selling and providing support and consulting services, which consists of obviously the Gluster component as a free and open source scalable network file system software-defined storage solution, which has really seen large deployments in the meantime. There are many large customers using it. The most common, also famous one is Facebook, which is running part of the infrastructure on top of Gluster. It runs on-premise in public and private cloud deployments, although the support cases that we are getting in touch with are most of the time on-premise, so on bare metal. It's a full stack clustering solution, including many important features like replication, quota, snapshots, geo-replication, so kind of a concept of having sites like in the Windows world, where you can asynchronously replicate your data contents. There are many other features, of course, that I don't mention here on my slides. You will find them on the very well and nicely provided documentation on Gluster upstream, as well as also from the Red Hat Gluster storage product on the Red Hat sites. Gluster runs on really every file system that just supports extended attributes, so it does not bring in its own file system, unlike other network file storage solutions, obviously. That has some advantages, but also comes with some limitations, which we will talk about later a little bit more, I think. But the good side definitely is that the requirements for running Gluster are really very minimal. You just need to have custom hardware and a file system that supports extended attributes. By default, XFS is used on the bricks, but you could use any other file system as well. So apart from this server stack, there's also a client provided, which is implemented as a Fuse file system. So it's not a native kernel client, but part of Fuse, which is commonly used and quite feature-rich as well. Then there's coming the whole set of automation and management utilities around there. There's a good integration with Ansible, and it supports a whole variety of access protocols, NFS, using the NFS Ganesha, and obviously SMP as well, which we're going to talk a bit more right now. So the fundamental architecture of Gluster is that you are providing the lowest data sets, which are bricks, which are most of the times just file systems or disks in your cluster nodes. And these bricks are grouped together into volumes, and the volumes then provide all the functionality that allow you to export these data sets to your clients and access them using protocols like NFS or SMB. Of course, there's not only one type of volumes. There are many, including distribution, replication, algorithms. There's arbiter volumes, dispersed volumes using erasure coding, so that you can keep your data sets a little bit lower than the overall requirement of data size. So it's a very flexible and very feature-rich way of grouping your data and exporting it over these volumes. Here in this picture that you see, you only have an example of a replicated volume. So that's probably the most simple setup, that you just have two bricks on each of the server nodes grouped together to a replicated volume. So the data set is always available on both nodes, and then exported as a volume, which then can be mounted, for example, using the Fuse client. On the architecture side, there's also another very nice property, which is the concept of translators. Translators exist both on the client side and on the server side, and they do provide a kind of similar functionality like the Samba VFS layer. So you can have a whole list of these translators in your stack, and each of these translators will just deal with a certain property of the whole set of calls that can be implemented. For example, on the client side, you see the first translator, which is hit by any operations, is the IOStat translator. Then the next one is the MD cache translator, open behind, quick read, and so forth, until finally the data is really sent out to the server. And then on the server side, you again have a huge set of these translators, which implement various properties. The last one being obviously here the POSIX translator, which is then really translating the IO requests to the disk. On the client side, the MD cache translator is really the one which is the most prominent one, because it needs to take care of providing caching functionality for all these heavyweight metadata operations, which Samba is doing. So, for example, inside this translator, there's an implementation which is specifically addressing the needs for Samba. You can see it's called or activated using this command line utility, cluster volume set, performance cache Samba metadata on. And if you enable this, then it will activate caching of, for example, the DOS attributes, extended attribute contents, the security anti-ACL. So in case you store the ACLs natively using ACL etc., which we'll also have a look at later on. So it will implement all these things and activate them. And along with this additional caching for metadata, there also comes a whole set of other important caching operations which need to be activated, that deal mostly with caching validation and the time to live of these cached objects and so forth. So there's a whole set of important commands which are well documented. I haven't put all of them here on my slides, but they're easy to really look up and part of the documentation everywhere. So this is really very basically and broadly the Gluster pieces of this Red Hat Gluster storage product. On the Samba side, you need to understand that RSGS, which is the application for Red Hat Gluster storage, is a layered product. What does that mean? It means that RSGS is installed on top of an existing operating system. So currently there is support for all the known RHEL variants. That also has another implication, because RHEL also has a very well and fine maintained Samba component. But given that we are a layered product, of course, we always want to have our Samba version take precedence over the RHEL variant one. So we are very keen and very busy with always really staying ahead of the RHEL version, so that not suddenly our small modifications that we do to our packaging and to our way that we install Samba is overridden by the rel variant. So that gives some maintenance pain for us, because we always need to make sure and test very well that we always bring the latest version to Samba to the customer and to the installation. But of course, it also is an advantage, because there's always a leading edge a version that really provides all the latest bug fixes and all the latest features that are developed in the Samba upstream world to the product. Then in Samba itself, there are two different ways, at least, to provide access to the cluster volumes. First of all, we have this fuse module, which is just whatever mounted as a local file system, which can then be re-exported like any other locally mounted file system. So nothing special about that. This always used to be the only way to provide Gluster in the early days. But then since, I think, 2013 or something, there has been a library created, and also a VFS module which uses this library, the gfapi library, which is a client accessor library. And this provides some advantages, because we can then obviously access the cluster volumes in some other ways, like just whatever locally accessing the fuse mount. We can provide some better behavior, particularly for large I/O. We can make use of some nice and important features, like we can provide an implementation of the getFileName call. We'll also have a look on slides about this later. So having this accessor library brings really various advantages, much better fine-grained control the way that we access the cluster volumes. But it also comes with some implications which are not to be neglected. And that is notably that given the Samba process model, where the main Samba daemon forks SMBD child processes to access then the VFS layer and to impersonate the user in order to enforce client kernel access control and these sorts of things. This forking model has the consequence that many instances of this gfapi client accessor library are forked on the operating system, and each one really having a quite heavy memory footprint, because each gfapi client loads the entire stack of these client translator modules that I've been mentioning into the memory. And given that you have the separation between users and the fork process modes, you easily end up with your memory quickly being exhausted with a relatively small number of client processes. So the usual way around this problem is to, again, use this fuse export way of accessing the cluster volumes. So there is some ideas and some early plannings in how we can avoid that by establishing or using an already existing proxy mode. We'll mention that later a little bit more. But right now, it's really important to have an understanding of this memory footprint issue. Then, as already part of the IBM Spectrum slides, of course, we also have requests from many customers that want to use Mac clients natively. They want to make sure to have an implementation of the create context and all these important pieces that the Mac clients enforce. The fruit module, thanks to all this wonderful work from Ralf Böhme and many others, provides a really nice and well-working implementation of that. It was just in the early days, or up to the recent months, only working on a local file system. So it was nicely working if you were using the fuse export, but it was still having some undeclared assumptions that it would always operate on a local file system. And by that, not really working very well with the VFS Gluster module, which only uses that accessor library in order to access the Gluster volumes. This has been sorted out right now, and it's now fully supported and also well tested. So we can provide good support for Mac clients as well. And a part of these VFS modules, of course, we also use CTDB, not only for the replication of the databases of Samba, but also for the high availability of Samba and the WinBind service. So Samba and WinBind are fully controlled by CTDB. in replica cluster storage, and also, of course, the floating public IP addresses. They are fully managed by CTDB. CTDB is providing this distinct GlusterFS volume for just the recovery log file, which is also the first candidate of one of the problems that many of our customers are seeing sometimes. So next sections are these named customer setup problems. The cluster volume for storing that recovery log file needs to be mounted, obviously, before CTDB starts up, so that it's not happening like CTDB creates this file locally in the local file system before the mount actually is really happening. So then it would just assume that it has full control over the log file, but in fact, it's not really operating on the clustered files system at all. And given that CTDB itself has no notion, no understanding of whether it is operating on a local file system or on a locally clustered file system, we needed to make sure that we have some ways to enforce always the mount happening prior to the CTDB startup, which can be nicely done with systemd, because you can make sure that your remote file systems are mounted prior to any startup of any other processes. But given the nature that replica cluster storage is a layer product, it also needs to operate nicely on RHEL 6 in the past months at least, which of course doesn't have systemd. So it was always a problematic thing to really get this right. And if people just start to reboot their entire cluster, they just expect that everything is coming up automatically. And this explaining them or convincing them that this is an assumption which is not always be the case, because sometimes the cluster volume for providing the recovery log file was laid out in such way that it could not start up until not all the nodes that are really hosting the contents of this data were started up prior to the CTDB startup. So it's somewhat difficult and sometimes delicate explanation effort that we need to do here. Also, what we have sometimes seeing, not so often though, is that people still do not wish or do not plan to properly separate the networks for pure CTDB communication, so the internal replication traffic, and also in particular the Gluster replication traffic, and the public-facing APIs, which are supposed to be on a different network. So when people then sometimes start to group all these networks together with using network teaming or some other technologies, it's very, very quickly happening that bad things happen in the event that one of these nodes is either disconnected or rebooted or something like this. Because, for example, we've seen setups where a customer were using DNS names which were pointing just to one of these IP addresses, sometimes even the wrong ones. And if part of their network infrastructure was taken down, like some nodes, it would then resolve just to inappropriate IP addresses, resulting to the unavailability of services. Could be CTDB, could be Gluster, or could be Samba, and really creating a very, very difficult, how do you say, a very, very difficult setup, because the client is then confused in such ways. For example, when it tries to reconnect a durable handle, the durable handle reconnect will fail, not because whatever our implementation is faulty or something like this, but sometimes because just Gluster is not pointing, or the IP addresses are not really properly pointing to the right endpoints in their infrastructure. So really having a very, very clear and very, very correct relationship between IP addresses and networks and DNS names is a very, very crucial and important component. And sometimes people are just not taking the necessary attention to that. Another thing we've sometimes seen is that the concept of CTDB as a storage for providing shared replication of credential carrying databases like secrets TDB and so forth is not properly understood. So although it's really made very clear in the documentation and in all the tools that we have, sometimes people just try to join every individual node to AD in case they want to join an AD, for example, which is obviously the wrong thing to do, because the cluster itself is assumed to be to appear to the clients as just one host. That means there's only one NetBIOS name, only one machine account, only one password for that machine account in AD. And as soon as they start to join the individual nodes, they're of course overwriting the account credentials all the time, sometimes even with different NetBIOS names. So if they don't have this set up very clearly, they just end up with a completely broken domain membership on all cluster nodes. So this tends to happen, and they're only very simple and correct way to work around and to avoid that is to have the same NetBIOS name on all your cluster nodes, to have the same workgroup name, obviously, if you want to join AD, on all the individual nodes. The same is also true for standalone setups. So it's not only a property of the clusters that are part or joined to an active directory domain, but also for standalone setups. People sometimes don't fully understand the fact that if they create some local users, these users are not really local in the sense of that they only exist on one node, given the nature that secret CTDB again is replicated on the cluster. They all really share the same account database. They all share the same SAM, and as thus also need to have the same workgroup and NetBIOS name on all these nodes. Otherwise, they easily end up with diverging SIDs, resulting then obviously in authorization failures of all sorts, because the SIDs then might not look the same on all these individual cluster nodes. The next one, and that's also a very common thing. So customer problems, customer issues mostly fall into two categories. They either are performance related or they are related to authorization. And POSIX permissions, that's also a very prominent one. And for this, I would like to hand it over to my colleague, Anoop.
Yeah, thanks, Günther. Yeah, so this is another common category of issues, like as we always know, dealing with POSIX permissions in conjunction with Samba, which has to be done very carefully. And with GlusterFS, the scenario, it's not different. So let's say we have to set up some ACLs for some users or some domain. So we start with the share root or some parent directory by setting up ACLs. These are generally done with the help of, from the POSIX side, with the help of setFACL and getFACL commands. GlusterFS being a POSIX compliant file system, it surely supports these commands. But by default, it doesn't include this option. So in order to set up ACLs with GlusterFS mounts, we have to additionally provide this ACL mount option so that ACL is enabled on a GlusterFS mount, and we can easily set up and perform these, execute these setFACL and getFACL commands. So let's say we properly set up some ACLs and everything is good. But at some point, we might realize that, we have this rich anti-ACL world and decide to use our ACL Extractor VFS module. So now things become a little bit complex. So with ACL Extractor in place, Samba by default performs this mapping from POSIX layer. So Samba keeps setting and evaluating these system ACLs along with these anti-ACLs. That's the default action taken by VFS ACL Extractor module. Now, in some cases where we can assure that access can only happen via Samba, we do have an option to this particular VFS module, like the ignore system ACLs option, which disables this best effort in mapping anti-ACL to POSIX world. And if we are switching between these particular configurations, like with and without VFS ACL Extractor modules, we have this problem. Like it can be the case that there are some default ACLs present from an older configuration without ACL exciter. And this default ACLs, if present, can overrule the mask applied by Samba when this particular ignore system ACLs option is set. So this conflict can result in access denied for users. So yeah, a probable solution is to just get rid of those POSIX ACL if we are sure that Samba is the only access pattern here and SMB is the only access pattern here and it goes through Samba. We can get rid of those and give the retry permissions, world retry permission, so that Samba can safely operate out of NT-ACL stored in as an exciter, like security.ntacl exciter. So that's the way we can tackle this problem. And this we have seen, yeah, we have been getting cases around this area. Yeah, so next slide. Yeah, so coming back to the performance bottlenecks or the performance issues that Günther was mentioning. So these performance issues can be broadly classified into two distinct areas, like the I/O, the proper I/O, and the metadata related operations. Let's look first at the role of I/O scheduling infrastructure that we currently have with Samba while connecting to GlusterFS in read-write scenarios. In case of GlusterFS, we have a basic building block called bricks, which constitutes a volume. So considering a write operation, as we have seen in the diagram in the earlier slide, with all bricks operating successfully, a write has to reach every replica brick where it resides. So yeah, of course, for this write operation, there are some basic aggregation techniques implemented using a write behind translator in Gluster to speed things up at a very basic level. But whereas when compared to read, read can always fetch data from the closest subvolume, whichever is closest to read. And talking about the internals in how we schedule this particular I/O, read-write, how we issue read-writes. The AIO implementation, the synchronous I/O implementation in our current VFS GlusterFS module, it is different from the AIO implementation that we have with VFS default module. So in VFS GlusterFS, we used to have the async APIs provided by the gfapi library, which we use to connect to GlusterFS. And the callback of these async APIs were being executed in a separate thread. So since Samba is majorly single-threaded, this approach of executing the callbacks in another thread was resulting in some crashes. So we had to register another event to notify about this async callback completion. So yeah, this resulted in a reduced performance as it delays this notification of the AIO completion. That is, it requires another event loop to mark its completion. So we decided to look at a solution to change the AIO implementation to use the pthreadpool infrastructure from that we can see with the VFS default module. Yeah, I will show some performance numbers in comparison to both these different infrastructure in the coming slide. On the other side, when we come to these metadata related workloads, it is often an incremental approach. So prominent calls around this area are like the stat calls, get etc calls, etc. So Samba, with its frequent invocations, makes it more difficult. Yeah, makes it more difficult for a distributed file system like GlusterFS to cope with. So either we minimize those metadata hungry operations from Samba, or have some aggressive caching from GlusterFS client itself. So later, maybe more meaningful to present ourselves as close to a local file system. So that's the way we have taken. But there are opportunities inside Samba to make requests more asynchronously, reducing serial wait time in post-processing of these results. Yeah, for when GlusterFS client is considered, GlusterFS has its default metadata caching translator called mdcache, which fits perfect to this use case. So we have been improving this component to include the caching for various exators, as mentioned earlier, user.dos@trib, user.dos stream, security.ntacl, to be fetched in advance to save some additional network calls. So along with exaters, stat information is often stored and sent from client stack, avoiding another set of network calls. Apart from metadata, we have an implementation for getReal file name. That's a VFS interface that we have with Samba, which improves the create time for files. And with VFS GlusterFS module, it currently does it via a virtual getExator code, which performs a case-insensitive search at the brick level, saving additional network calls. That would originate in the absence of such an implementation. Next slide.
Yeah, sorry, I already changed the slide.
Yeah. So yeah, this is basically the comparison in numbers between the two different IO scheduling infrastructure. So on your left side, we can see a graph or a chart showing the numbers, comparison in numbers for the read operation. And the lighter shade is the one with async libgfapi. That's the older implementation. And the darker shade columns are for the pthreadpool implementation. That's a new one. And comparison is done for 3 different block sizes: 64K, 128K, 256K, and similarly for right on the right hand side. And the throughput is displayed in GB per hour, and it is done on a 12x2+1 arbiter Gluster volume with Samba on top of it, spread across 3 nodes with CTDB. And the thread count is 12 with a block count of 16K. And the mode used here is random. So this is basically based out of some results which we have received from one of our customer and their disk performance tool that they have used. So we can see the increase in throughput with the pthreadpool infrastructure in both cases, in read and also in write. Yeah, next slide. This is another column chart which shows the improvement with the GlusterFS client caching with the help of various caching translators in Gluster while listing a large directory. So here we have used a 12x2+1 arbiter volume spread across 4 nodes with CTDB. So we have used the assembly client with 16K 1 KB files in a directory, and the time taken to list it using the assembly client. So you can see 3 different comparisons. The first one is with the plain default volume options with the GlusterFS volume. There are no specific caching options enabled. And the second one is with read ahead translator and the parallel read. And the third one is with mdcache and all other dependent options, like it's not just enabling mdcache, we need to deal with all other caching validation options also. So yeah, we have all. The third one is with all the options enabled. And the comparison, I have included the warm cache and cold cache comparison. Like we clear the cache at the first run and try to list the directory, and we list it immediately second time, so that caching is in effect. Here also we can see the reduce time when various options or the volume settings are applied on the volume. Yeah, next. Yeah, this is another area that we have to improve, or is an ongoing effort, which is a recursive listing of large directory tree. So with large directory tree, we mean with depth level up to depth level of like 10 or 100, etc. So yeah, we have a recent proposal from GlusterFS, which is an improvement basically in the distribution layer of GlusterFS. It is an improvement to the current prefetching logic that we use in DHT, which is the distribution layer in GlusterFS. It is making use of the current prefetching logic to efficiently return back the radial buffer by filling it to the maximum. So performance.radial cache is the volume set option, and it is still a patch in review. But the native client, which is the Fuse client improvements, have showed an enormous improvement up to 100%. And when it comes to Samba, we are yet to see or yet to explain this effect, this improvement. We have to test it and see how much improvement we'll be getting out of it. Yep. Now to Günther.
Right. We mentioned this distinction between the Fuse re-export and the VFS GlusterFS module. So of course, we also wanted to bring some of these advantages that the VFS GlusterFS module brings also to the Fuse module. Notably, the availability of the getRealFileName call, which is really an enormous save up from all these expensive case folding operations in order to detect the proper case file name is written on the file system. And GlusterFS provides an API for that just by providing a virtual extended attribute called GlusterFS :get_real_filename :filename. And this, of course, can very easily be queried from the Fuse layer as well. So yeah, thus creating a very easy and slim VFS GlusterFS Fuse module as a new vehicle to access this information was a very easy thing to do. Later on, we got aware that, of course, we need to address the file ID problematic. So there is the file ID VFS module, which is meant to provide algorithms to generate unique file IDs. File IDs in Samba consist of device IDs and I think an inode ID or something like this. So these two components. And if you have a clustered file system, then the likelihood that you have differing device IDs in all the cluster nodes is very high. And for that reason, we need to make sure that we have absolutely unique file IDs. File IDs themselves are used as a key component in order to do file locking in the file server of Samba. So algorithms and mechanisms, including some caching so that we don't read this information too often, have been brought also to this newly designed VFS module. And it's very straightforward to add it to your stack. Just no additional options are required. Everything is nicely documented. I mean, there's really nothing to do wrong here. You just add it to your VFS object stack in the configuration, and then you can leverage all these things. Of course, you still have these context switches that Fuse modules always come with, but this most of the time are the most unlikely performance issues that you might encounter. Anoop? Anoop? There? Okay, you can't hear him, so I'll just cover. Okay. Ah, yeah, there you are.
Okay. Yeah, so this is another a new VFS interface that we had that got recently added. Yeah, the motivation behind this was we happened to see a regression with GlusterFS as the backend. And yeah, we got to know that a particular FD flag, which is the or non-block flag, was being set set by bypassing the VFS layer. So it basically ended up like errors while trying to open or create files in Windows. So yeah, the basic root cause here was that this particular on-block flag setting was not going through the VFS layer. So we introduced a new VFS interface called Samba VFS FCNTL, which will help us to have this particular FD flag setting go through the VFS towards the backend file system, and the backend file system, their own modules can implement their own functionalities. So introducing this VFS FCNTL interface, there are various FCNTL flags that needs to be considered, and these flags are currently automatically detected during Samba configuration in the compile time. And I think it is the only VFS interface macro with variable arguments right now in Samba. And right now there is only one invocation for this particular interface, which is from open file function inside Samba while opening the file. And in GlusterFS, the VFS module for GlusterFS, we receive as soon as the implementation for this particular VFS interface, we just return true for this particular flag. That's the hack that we are used currently, because we do not have an API right now to exactly set FD flags through an API. So yeah, that's why we have used a hack right now to return true for this particular flag. Yeah.
Right. So the last section of our presentation about the ongoing developments around Samba in this area. So first of all, I mentioned already this problem that we sometimes encounter, that if during ongoing I/O one of the nodes is disconnected or even rebooted or switched off or something like this, people encounter durable handle reconnect failures from their clients. And there's a patch from Ralph who has also identified this problem when working on his customer cases, that you can just disable these reconnect checks, which basically do compare stat information with the stored cookie information that Samba is maintaining during in its databases during the time of the disconnect. So this information is compared. The comparison fails because Gluster, under some of these circumstances that I mentioned earlier, might deliver incorrect information, which can be avoided once the network is properly set up and the networks are better separated, so that Gluster can provide better and more accurate information. But nonetheless, this is an area where we need to fully check the correctness of these checks in the case of Gluster disconnects. That's definitely something we need to explore more. The slow directory listings that Anoop has mentioned, and the enormous impact that this work in progress patch set, which is currently under testing, brings, that's something we need to explore more. Also the sometimes the difficulties when you use the gfapi approach using the VFS GlusterFS module, the memory consumption issues. There are designs and ideas how to use an already existing proxy layer in order to avoid this heavy footprint of the initialization of the client translators back all the time. There's work ongoing, of course, in the multichannel area, which we are really finishing since a long time. So the rework areas, the oblog leaf replay, where my colleague Sachin, who's also up talking next, will maybe explore a little bit more. He has provided a patch set for this, which is currently under review. We have the testing aspects using socket wrapper and the integration with CTDB, which is an important aspect to make sure the IPs are not whatever split spawn over various cluster nodes. These are still areas we need to work on. Of course, the witness interface, we provided a prototype back in 2015, me and my colleague Jose. but that all that work was halted because at the time we only had an asynchronous DCRPC server, which is a prerequisite available in Samba 4. Now with this nice work from Samuel, from SUSE, we most likely will have this available, and I think they also are working on their own implementation of the witness service. Whoever is first with that, that's really great. Then we have finally that a much nicer and yeah, more programmatic way of transparent failover available in Samba. And last but not least, all the automation and CI aspect. That's a very important topic. Where Sachin and Michael on their next talk will discuss about. So they have really made some very nice progress there, and will show it